Hello again, and welcome to Quantum on the Treadmill. As learn about the history of quantum, it seems like most of the focus is on light and not sound. As a musician, I'm obviously more interested in sound. I thought I'd ask a few questions, cube out phonons versus photons. As always, almost all of this video was created by AIWGEL. I was on the treadmill. I hope you enjoy.
The hidden quantum revolution you never hear about, how sound changed physics.
Most people know the story of the photon.
If you followed my writing, you probably heard me tell it dozens of times. Max Planck quantized light to solve the ultraviolet catastrophe. Einstein transformed that mathematical trick into the photon. Bohr used quantum ideas to explain the atom. From there came Heisenberg, Schrödinger, and eventually the quantum computers being built today. It's a remarkable story, but there's another quantum story that receives far less attention. It doesn't begin with light, it begins with sound. And in some ways, I think it's even more surprising. Before quantum sound was just a wave, for thousands of years, people understood that music and sound had deep mathematical structure. Pythagoras showed that simple numerical ratios produced harmonious musical intervals. Galileo connected vibration frequency to pitch. Newton described sound as pressure waves traveling through air. By the 19th century, the picture seemed complete. Sound wasn't mysterious, it was simply a wave moving through matter. Unlike light, sound couldn't travel through empty space. It needed air, water, steel, or some other material to carry the vibration. Case closed, or so everyone thought. Planck solved one problem. In 1900, Max Planck was trying to explain the spectrum of light emitted by a hot object. His solution changed physics forever. Energy, he proposed, was exchanged only in discrete amounts, not continuous, not infinitely divisible, discrete. The strange part is that Planck didn't believe nature was actually discrete. He viewed quantization as a mathematical device that happened to match the experiments. Like many revolutionary ideas, it solved the problem before anyone fully understood why it worked. Einstein soon took the next step. If energy came in packets, perhaps light itself behaved as packets. The photon was born. But what about matter? While physicists were celebrating the success of quantum theory for light, another puzzle was quietly emerging. When scientists measured the heat capacity of solids, the numbers didn't agree with classical physics. According to 19th century theory, atoms vibrating inside a crystal should store far more thermal energy than experiments actually showed. Something was missing. In 1907, Einstein returned to the idea of quantization. This time he wasn't talking about light. He imagined every atom inside a crystal behaving like a tiny quantum harmonic oscillator. Instead of vibrating with any possible energy, each atomic vibration could occupy only discrete energy levels. The agreement with experiment improved dramatically, but it still wasn't the full story. The orchestra, not the instruments. A few years later, Peter Debye realized the deeper truth. Atoms inside a crystal don't vibrate independently, they vibrate together. Imagine a stadium full of people performing a wave, and no single person is the wave. The wave exists only because thousands of people move together. Or picture a guitar string. When you pluck it, every point along the string moves. The note you hear isn't produced by one molecule, it is the collective motion of countless atoms acting as a single system. A crystal behaves the same way. Millions upon millions of atoms connected like tiny springs support standing waves that extend across the entire material. The vibration belongs to the system, not to any individual atom. Then physics did something extraordinary. In the 1930s, physicists realized these collective vibrations behaved mathematically just like particles. Not particles made of matter, not elementary particles like electrons, not photons traveling through space. Instead, each allowed vibration mode carried discrete packets of energy. They gave these packets a name, phonons, the quantum of sound. This may be one of the most underappreciated conceptual leaps in all of physics. The phonon isn't a tiny ball hidden inside a crystal. It's the quantized behavior of a pattern. The particle is the vibration itself, a different kind of reality. This is where the story becomes philosophically fascinating. A photon can exist by itself, a phonon cannot. Destroy the crystal and the phonon disappears. The phonon exists only because the underlying system exists. Physicists call objects like this quasi-particles. They aren't fundamental building blocks of the universe. They're emergent phenomena, stable, quantized patterns that behave so much like particles that treating them as particles becomes the simplest and most powerful way to describe reality. That idea changed condensed matter physics forever. Soon came magnons, excitons, polarons, plasmons, Cooper pairs, and an entire family of quasi particles that now dominate modern materials science. Why this matters today. Without phonons, much of modern technology would be impossible to understand. They explain how heat moves through materials, why semiconductors behave the way they do, how superconductors emerge, how lasers and LEDs operate more efficiently. Even today's quantum computers spend enormous effort managing interactions with phonons. Sometimes phonons are the enemy, introducing decoherence that destroys fragile quantum states. Sometimes they become the resource, carrying or storing quantum information themselves. Scientists can now create individual phonons, trap them, count them, entangle them, and even use them as components in quantum technologies. The quantum mechanics of sound has become a frontier of engineering. The lesson I keep coming back to, the history of quantum mechanics is often told as a sequence of discoveries about particles. I think there's a richer story. Planck taught us that energy is quantized. Einstein taught us that light is quantized. Bohr taught us that atoms have quantized states. But phonons taught us something even more profound. Relationships can be quantized. The universe isn't composed only of things, it is also composed of patterns. Sometimes those patterns are so stable, so predictable, and so deeply woven into the mathematics that they deserve to be treated as objects in their own right. That may be one of the deepest lessons quantum mechanics has to offer. And it all started with something as ordinary and as extraordinary as sound.